Hello and a good day to all. Previously, we have looked into the properties of open channel and also uniform flow. In this slide, we're going to look into rapidly varied flow. For rapidly varied flow, it have a pronounced curvature of the streamlines, means that there is a curve in the streamline and it does not follow a smooth and straight flow path. Rapidly varied flow may become so abrupt that the flow profile is virtually broken, resulting in a state of high turbulence. Normally, rapidly varied flow occurs in a short distance or length along the channel. Example of a rapidly varied flow is the hydraulic jump. Often the case for rapidly varied flow, the flow transition between deep and slow flow. In other words, the subcritical flow with fluid number less than 1 to become shallow and fast flow with the fluid number more than 1, which is supercritical flow. In terms of the characteristic of rapidly varied flow, the curvature of the flow is so pronounced that the pressure distribution cannot be assumed to be hydrostatic. And this rapid variation in flow region often occurs in relatively short distance. When rapidly varied flow occurs in certain transition structure, the physical characteristics of the flow are basically fixed by the boundary geometry of the structure as well as by the state of the flow. In terms of the velocity distribution coefficients, namely alpha and beta, they are usually far greater than unity and cannot be accurately determined. This figure here shows the profile for an example of rapidly varied flow. So in this profile here, A1 is usually the one with which the flow is much faster and flow under supercritical, while at section 2, A2, the flow becomes subcritical with the slower velocity. This profile is an example of hydraulic jump. In terms of the continuity, the volume flow rate Q equal to VA is the same at each of the section. The velocity can thus be related to the cross-sectional area and hence the depth by equation 1, where V equal to Q over A. In terms of the momentum, we need to consider the momentum principle, which is the net pressure force will be equal to the rate of change of the momentum. In other words, the pressure at section 1 multiplied by the area at section 1 minus the pressure at section 2 multiplied by the area at section 2 will be equal to the density multiplied by Q multiplied by velocity at section 2 minus velocity at section 1. So from this, then we can simplify it to become the forms in equation 2. Then taking the depth as half of the h, from there the area will be equal to h multiplied by the width of the channel, which is B, and the Q will be equal to the Q per unit length of the width multiplied by B, which is the width of the channel. Then the momentum principle will be reduced to 1 over 2 rho g h1 square b minus 1 over 2 rho g h2 square b equal to rho q square b in the bracket 1 over h2 minus 1 over h1. So if we divide all by rho b, then we can simplify further by dividing with g h1 minus h2. We can get the expression as in equation 3. If, let's say, we take the depth ratio h2 divided by h1, then we divide through by h1 square, we can simplify it further. And since your q equal to vh and your right hand side is v1 square over gh1, or the Freud number at section 1 square, hence we get the forms in terms of equation 4. Then from this we can rearrange it so that we get the form in equation 5. This is a quadratic equations for the depth ratio h2 over h1, and its positive root, if we try to solve this quadratic equation, will give you the expression in equation 6. Then, since the surface level Zs equal to Zb plus h, Zb is the level at the bottom of the channel, then the surface elevation part of the total head can be subdivided into bed elevation Zb and the depth of flow h. So in other words, your h or your head is equal to Zs plus v square over 2g, or in other words, Zb plus the small h plus v square over 2g. So from there, we can get the specific energy. In this case, the specific energy is relative to the bed of the channel. So we actually remove the terms Zb. Hence, we get the E equal to h plus v square over 2g. So in other words, the capital H is actually equal to Zb, which is the level at the bottom of the channel, plus E. If the bed is horizontal and we choose to measure the vertical coordinate Z from it, then we can take the level for the bed Zb as a datum or equal to 0. In this case, then your H will be equal to E. If, however, the bed varies in height, then the total head is constant. With the assumption that the total head is constant, the increase in Zb will result in the decrease in the specific energy E. So, in other words, the specific energy in a channel section is given by this equation, E, which is the specific energy, equal to Y plus V squared over 2G. When the depth of flow is plotted against the specific energy for a given channel section and discharge, we can get a specific energy curve as shown in the figure. In this curve here, we have the y-axis representing the flow depth and the x-axis actually representing the energy in the channel, in the flow. What we can deduce from that plot just now is that for a given specific energy, there are two possible depths, namely the low stage y1 and the high stage y2. So the low depth is called the alternate depth of the high depth and vice versa. At point C, the specific energy is the most minimum. This depth corresponds to the critical depth, YC. Any depth that is greater than YC, the flow is subcritical, while any depth lower than YC, the flow is supercritical. We can use this curve to estimate the critical depth. To use this curve, first we need to determine what type of channel shape it is. Either it's a rectangular or a trapezoidal or a circular. So if let's say you have a trapezoidal section or a rectangular section, then you have to use the axis on top of the curve to calculate the z divided by b to the power of 2.5. From there, once you calculated the value of this z divided by b to the power of 2.5, you can pull down the vertical line to touch the corresponding curve. If let's say it's a rectangular curve, then you touch the rectangular line and then you read what is the value on the y-axis. The value that you get on the y-axis will give you yc divided by b, which is the width of the channel. So if you want to get the critical depth, which is the yc, whatever value that you get from the y-axis, you need to multiply it with the width of the channel. Only then you can get the critical depth. This curve looks almost similar like the curve to find the normal depth that you have seen in the previous lecture. But do not confuse between these two curves. One is to determine the normal depth, and this one here is to determine the critical depth. So, in terms of the criterion for the critical state of flow, at critical state, the specific energy is minimum. In other words, your dE over dy will be equal to 0. So from there, v squared over 2g will be equal to d over 2, or in other words, your v divided by square root of gd will be equal to 1. So the expression of v divided by square root of gd is actually the fluid number. Just now, for the curve to find the critical depth, we have the expression of z divided by b to the power of 2.5. To find that z value, it is actually equal to q, which is the discharge, divided by the square root of g, which is the gravity. So once you manage to find this z, you divide it by the width of the channel to the power of 2.5, you will get the value in the horizontal axis. Then you can, like I mentioned just now, you can pull the vertical line to touch the appropriate curve according to the shape of your channel, and you read the y-axis. Whatever value you get from the y-axis, you multiply by the width of the channel, then you will get the critical flow depth. Let us take a look at this example. A 3-meter wide rectangular channel carries a discharge 17 meter cube per second at a uniform depth of 1.7 meter. The Manning's N value is equal to 0.012. Determine the channel slope, critical slope, and the fluid number. So, to solve this example, we use the Manning's equations. Manning's equation, the expression is Q equal to 1 over N AR 2/3 square root of S. So the first part of the question is to find the channel slope, which is S. We just need to substitute all the given value from the questions into the Manning's equation. So if you substitute that, you'll find that the only variables that is unknown is the S, which is the slope. But doing calculation, you will find that your S is equal to 0.0022. Now comes to the main focus of this example, which is to find the critical depth. To find the critical depth, first we need to find the Z. In this case, the Z is equal to Q square root of G. Q here is the discharge equal to 17 divided by 9.81 power of 1 over 2. So you get the Z as 5.43. Once you manage to find the Z, the next thing is we divide the Z with B, which is the width of the channel, to the power of 2.5. So from there, it will get you as 5.43 divided by 3 to the power of 2.5 will be equal to 0.348. With this value, we go to the horizontal line of the critical depth charts. From there, we pull down our vertical line to touch the appropriate shape. In this case, is rectangular. Then from there, you read what is the value on the vertical axis. In this case, the vertical axis YC over B is 0.5, and since the channel width is given as 3, the critical depth will be 0.5 multiplied by 3, which will get you as 1.5 meter. Then the next thing is find the fruit number. To find the fruit number, we can use the expression of Q square B divided by G A to the power of 3, and all the expression we power it with 1 over 2. Substitute in, you'll get you the fruit number value as 0.67, which is less than 1. This is considered as subcritical flow. Next, we're going to look into hydraulic jumps and what happens to the energy during hydraulic jumps. In the figure shown in this slide, during hydraulic jumps, there are actually two depths. One is Yi, which is the initial depth before the jump, and another one is Ys, which is the depth after the jumps, or in other words, the sequence depth. In terms of the energy, as we can see from the figure on the right hand side, a smooth is not possible during the jump, because if this were to occur, the energy would vary according to the root of A, which is at the initial depth, then move to B, then move to C on the curve. At B, the energy would be less than at C, corresponding to the downstream depth, which is the sequence depth. Therefore, during the jump, a rapid depth changes occurs corresponding to the route of A to C directly without going through the B on the energy curve. So, for a given channel and discharge, there is a unique relationship between the sequence depth and also the initial depth. To find the initial depth, if let's say we know the sequence depth, then we can use the top equation, which is y initial equal to y sequence divided by 2 in the bracket square root of 1 plus 8 beta fruit number at the sequence depth square minus 1. On the other hand, if let's say you are to find what is the sequence depth, you can use the expression of y initial divided by 2 in the bracket square root of 1 plus 8 beta multiplied by the fruit number at the initial depth square minus 1. To find the energy loss through the jump, it can be given by the expression below, which is delta E, which is the energy loss, equal to the y sequence or y2 minus the y at initial depth or y1 to the power of 3 divided by 4 multiplied by the initial depth multiplied by the sequence depth. To find the length of the jump, L, which is an important parameter affecting the size of a stilling basin, we can use this chart by the US Bureau of Reclamation. So in this chart, to find the L, first we need to calculate what is the fruit number first. So the fruit number is given on the horizontal axis. Once we manage to calculate this fruit number, then we can pull a vertical line to touch the curve, and from there we can read what is the value of your length divided by the y2. So in other words, to find the length of the jump, whatever value that you get on the vertical axis, you have to multiply by the y2 or the sequence depth. In terms of the type of the jumps, this one here actually depending on the value of the fruit number. If the fruit number values between 1 and 1.7, this is what we call an undulating jump. In this case, the water surface is undulating with very small ripple, and the sequence depth ratio is very small and is practically 0. If the fruit number is between 1.7 and 2.5, this is what we call weak jump. The surface roller makes its appearance when the fruit number is 1.7 and gradually increase in intensity towards the end of this range, that is when the F equal to 2.5. For oscillating jump, the fruit number value varies between 2.5 and 4.5. This category of jump is characterized by an instability of the high velocity flow in the jump, which oscillates in a random manner between the bed and the surface. Then you have a steady jump with a fruit number value between 4.5 and 9. In this range of fruit number, the jump is well established and the roller and jump action is fully developed. In terms of energy loss also, it ranges between 45% to 70%. Strong or choppy jump happens when the fruit number is more than 9 and the water surface is very rough and choppy. In this case here, the energy dissipation is very efficient with values greater than 70%. The figure on this slide shows the different types of hydraulic jumps. So why is it that we purposely want to induce hydraulic jumps in the designs of hydraulic structures? First, in terms of the practical applications, it is used to dissipate energy. In other words, to reduce the energy at the downstream. For example, for structure like dam, weirs, and other hydraulic structure, this is to prevent scouring. It can also be used to recover head or raise the water level on the downstream side of a measuring flume and thus maintain high water level in the channel for irrigation or water distribution systems. Hydraulic jumps also promote mixing of chemicals used for water purification and also for the aeration of water for city water supplies. In this example, you are given a spillway which discharges a flood flow at a rate of 7.75 meter cube per second per meter width. At the downstream horizontal apron, the depth of flow was found to be 0.5 meter. What tailwater depth is needed to form a hydraulic jump? If a jump is formed, find its type, the length, head loss, and also energy loss as a percentage of the initial energy. So, given the questions, the Q is 7.75 meter cube per second per meter, and the initial depth of Y1 is 0.5 meter. So, to find the velocity, since Q is equal to AV, to find the velocity, V is equal to 7.75 divided by 0.5, you will get 15.5 meter per second. Hence, the fluid number will be F1 will be equal to V divided by the square root of GY1, or in other words, 15.5 divided by square root of 9.81 multiplied by 0.5, you get the fluid number as 7. To find the sequence depth means that the depth after the jumps, we use the equation that you have seen in the previous slides, where Y2, which is the sequence depth, divided by Y1, which is initial depth, equal to 1 over 2 in the bracket -1 plus square root of 1 plus 8 multiplied by the fluid number square. If we substitute in the value, it will give you as 9.41. So to find the sequence depth Y2, it will be equal to 9.41 multiplied by the Y1, which is 0.5, which will get you as the sequence depth of 4.71 meter, which is the required tailwater depth. Since the fluid number value is 7, hence the type of jump is steady jump. Then, to find the length of the jump, since your fluid number is more than 5, from the charts given by the US Bureau of Reclamation, it will get you as 6.1 multiplied by Y2. So from there, the length of the jump is equal to 6.1 multiplied by 4.71, which will get you as 28.7 meter. For the energy loss or head loss, the expression is Y2 minus Y1 to the power of 3 divided by 4 multiplied by Y1, Y2. If we substitute in the value, it will give us as 7.92 meter. Then to find the ratio of the energy loss with the initial energy, we have to find the energy at the initial depth first. In this case, the specific energy at initial depth is given as Y1 plus V1 square over 2G. If we substitute in the value, it will give us 12.75. Then the ratio between the head loss or energy loss with the initial energy is 62.1%. Now we're going to look into various types of hydraulic structures that involve rapidly varied flow. The first one is the broad crested weir. For the broad-crested wheel, let's say if we neglect the energy losses between section 1 and section 2, then the total energy at section 1 should be equal to total energy at section 2. But because at section 2 we have the wheel there with the height of Z, then the energy at section 1 will be equal to energy at section 2 plus the Z. The bottom special energy graph shows the energy for the broad-crested wheel. Then from there, we can get the expression for the discharge for broad-crested wheel. The general form of these equations, which included the coefficient of discharge C, is as given as Q equal to 2B, where B is the width of the broad-crested wheel, divided by 3, multiplied by C, the coefficient of discharge, multiplied by square root of 2G divided by 3, multiplied by Y1, which is the floor depth at the initial section, section 1, power 3 over 2. The next structure that involves rapidly varied flow is the Venturi Flume. For Venturi Flume, at the throat, the state of the flow is critical. So, to find the energy for a rectangular channel, the energy E is equal to 3 over 2 multiplied by YC, where YC is the critical depth, and the Froude number is equal to 1. So from there, for practical use, we can find the discharge through a Venturi flume by using the expression of Q equal to B. B here is the width of the throat, multiplied by C, which is the coefficient of discharge, multiplied by square root of G, multiplied by Y1. Y1 here is the floor depth before entering the throat, to the power of 3 over 2. That's all for this session of lecture. Thank you.